Hi everyone, this is gonna be a recorded version of my talk at the UTERC 2025. Um, my name is Howard. Today I'm going to talk a little bit about my work on improving wind turbine efficiency with synthetic jet actuators. So, start with a little bit of background. We've been using wind power for a pretty long time now, back all the way into windmills. The main difference is back then we basically just harnessed the raw mechanical power, using it to grind grains, etc. Nowadays, we tend to convert it to electricity and then to sometimes be converted to thermal or even back to mechanical energy once it gets to the destination. There are two main types or categories of wind turbines. Horizontal axis wind turbine is the one on top. These are more traditional that we might recognize. The axis of rotation is all horizontal into the page, as you can imagine. The one below are the other category, a vertical axis wind turbine. These are actually pretty interesting. Um, the video on the right shows kind of like how they work. This is actually based on, or the wind turbine is in located at a campus in California. Um, Basically, instead of having horizontal axis of rotation, for them they're vertical. Some of the pros you get is the angle of attack or the wind direction doesn't matter. Um, However, we don't see vertical axis wind turbine that much because even though the wind direction doesn't matter, the efficiency is actually lower than a well-placed traditional horizontal wind turbine. And also it doesn't scale well when you try to increase the scale. For both types of wind turbine, there's a couple of features that they both share. The tower, which basically creates the ground clearance, you need to mount the turbine blades, which is what generates the lift, and then also generates electricity based on the generated in the nacelle. Starting with the wind turbine blade, if you cut across it, kind of create a 2D cross section, it actually resembles a airfoil, similar to what you expect on the wings of an airplane. And similar to the wings of an airplane, the airfoil, when you increase the angle of attack or pitching upward, you generate more lift, but also leads to stalling, which on a plane you will not be able to take off. And on a wind turbine, you basically generate less electricity. So one of the ways to get around this is by using a little device called synthetic jet actuators, SJA. On the upper right, I have a schematic diagram drawing of the operation. The way that works kind of similar to your human lungs. They alternate between ingestion and expulsion cycle. During ingestion, the cavity volume kind of expands, draws air in, and during expulsion, it squeezes it back out. One of the main benefits with these SGA devices is that it doesn't need additional fluid source or reservoir. You don't need a bunch of pipings or like a compressed gas tank to operate. You just need your surrounding fluids. Um, so this is from some of the alumni in my lab. Um, so on an airfoil, when applied correctly, so without the control, you can see the wake, uh, the black voided regions basically separate the flow, and this is a fully stored airfoil. The wake size are also pretty tall and unsteady, as indicated by the red arrow. With adequate control, we first suppress the flow separation and also the wake behind the airfoil is also significantly reduced, especially the height. Now, this has two main benefits. First, it improves the power output of the first wind turbine. And second, quite often when we have a wind turbine farm, we have like layers of rows and rows of different wind turbine. Being able to reduce the size of the wake after the wind has passed the first wind turbine can also improve the performance of the downstream wind turbines. My work comes in focusing more on the tower side of the wind turbine. This can be somewhat, simplified into a circular cylinder. It's not even quite a simplification because the actual geometry is quite often a 2D cylinder. The Reynolds number is 3900, a little low, but it's still turbulent. And quite often, instead of looking at the cylinder from the side, we kind of lay it down, so create almost like a top-down view. This is because, so if we just look at it on the sides originally, it would actually hide some of the features from the outer vortex. Having this top-down view gives us better sense of the structures. The boundary condition is pretty straightforward. Velocity inlet, pressure outlet. We're using a periodic boundary condition on the front and back here, or basically the top and the bottom of the cylinder. This gives us a nominally two-dimensional flow, but the flow itself and also the simulation is fully 3D. We're mainly doing this to reduce the need of the interference of the ground effect. So the simulations ran in OpenFOAM. It's largely simulation with the well model, and the model is second order accurate. So I'm going to start the result section with a bit of a Q criterion contours animation. Quite often this is used to look at the flow structures around certain geometry. On the left, we have the isometric view. On the right, we have side view, which is basically the same as the top-down view. So starting with the left, we have a laminar separation, but then the flow transitions to turbulent. There's quite a lot of streamwise and spanwise fluctuation. And the flow is overall quite turbulent. On the side, however, even though the flow is turbulent, you can still see a periodic flapping motion. So this is actually the wake, otherwise known as von Karman shedding. This is actually the same or pretty similar physics to what you see on the wake of an airfoil on an airplane. Another thing that we can also see is the cage instability, basically the shear layer breakup. Now, Q criterion contours animations are impressive visually and could give us insight into flow structures, but quite often we also want something more quantitative. So one of the things we looked at is the energy cascade, or turbulent energy cascade. We want to make sure that the simulation is turbulent after all. So we have a bunch of probes, especially in the shell layer and in the wake, and overall compare pretty well with the turbulent energy cascade rate of -5.3. So the FES, the vortex shedding frequency, is basically the same as basically the wake, what we saw on the last slide. We have a second peak. That's because there's two sides of the cylinder, right? The top and the bottom. So each side of it actually generates a wake shedding. So that's why we have a duplicate of a double the frequency. If we look close to the edge of the shear layer, we also see the broad band of the shear layer frequency spectrum, roughly in order of magnitude higher than our wake. Well, why are we looking at all those frequencies, right? The reason is that we need to look at what we're trying to control before we attempt to control it. And this is kind of where the frequency comes in when we attach the SJA, synthetic actuator. So this SJA diagram picture on the lower right is actually what my colleague uses in the lab on an airfoil. Pretty small, 20 mil, and they're also very lightweight. I think somewhere between 6 to 16 grams. Has a lot of potentials. Some of my past work has shown that if you kept everything else the same, but just changed frequency, you get quite significantly or quite different flow structures. So this is why we have to be pretty precise and careful with the frequency before we attach the SJAs. since there are certain structures that are more beneficial for flow control. The way these works, so we put for now just two, one on top, one on bottom. This kind of like a cross section of the symmetry or the midspan. And this is sort of how it looks in us during the simulation. So even though the cylinder diameter is 50 times the diameter of the SJ exit, uh, the sole SJ actually has quite significant impact. You can kind of see the vortex ring as it gets expelled, and then it creates kind of almost like a ripple effect. So some of the future work are basically some of the works I'm working on now. So burst modulation, we have two frequencies that we're trying to target. Usually SJ operates at a higher frequency than these two, so we want to modulate them, and we also don't want to swap out SJs when we're just want to target a different frequency. The burst modulation allows us to do that. Then once that's done, so far we'll have two SJ, one on top, one on bottom. What happens if you have an array, let's say 5 on one side or 10 evenly distributed, 5 on top, 5 at the bottom? How closely do we have to pack them together? And also, what kind of span-wise coverage an array can generate.